Alberto is a CTO and architect in the space of real-time audio video focused on IoT, VoIP, and WebRTC. As our world becomes ever more globalized, real-time audio video technologies become more important and leveraged. This is why it is important to know how to properly architect real-time applications, and that's exactly what Alberto is going to talk to us about. So, Alberto, please welcome and take it away.
Thank you so much, Baclav, for the introduction. So yeah, I'm going to talk about architecting live video applications. Okay. So yeah, the agenda today is going to be about, well, first I will introduce a little bit of WebRTC, which is a very common protocol for low latency applications, real-time applications. And then I will talk a little bit about the challenges and some alternatives on how to build, architect WebRTC applications, specifically some basic architectures about the CPU and MCUs. And then at the end, I will get a bit more in depth into like scalability, optimizations, and other things that can be done potentially in the future to optimize your architecture. So yeah, WebRTC is basically a open framework for web that enables real-time communications. It was built designed years ago, but what has been officially standardized in 2021. And yeah, it's being used. I've seen being used in many of the companies, all the companies I'm showing just right here. So it's pretty popular for low latency. So as you can see, for example, here in this image at the bottom right, there are alternatives, for example, for streaming that are like HLS or Dash that are good for like 5 seconds latencies. But if you are aiming for something that needs to be sub-second, yeah, WebRTC is one of the main protocols used for that, and that's all the architecture comments and those things will be focused on this protocol. And yeah, it's not only video chat, it's not only video calling. There are many use cases. Can be professional events, live broadcasting, telepresence. So could be remotely controlling cars, for example. We could use WebRTC as well for that. So there are really many use cases. It's not just Google Meets and those video conferencing tools. So yeah, in two very basic steps, WebRTC works by has a signaling server. Here we call it signaling, where it says signaling and messages. That's like a server where we exchange communication between participants, and we make sure the participants can connect at the right time, and we know how to coordinate things. And WebRTC actually doesn't define this piece. What WebRTC defines is the video and audio communication. So there are two very the main APIs used are the Media Stream API and the RTC Pure Connection API that I'm showing here at the right. And those are mainly the two basic steps you need to do to have like a video call flowing for a one-to-one call. In the first step, you capture the audio or the video or both. And in this case, we use the what is called the get user media method. And that is basically capturing your stream like I'm using right now. And then there is the other part, which is the core of the WebRTC protocol, which is the RTC Pure Connection, which will allow us to send and receive video from between participants. And here I just briefly describe the main steps. So you would create something called a RTC Pure Connection, which would be the connection that allows us to send video and audio using UDP. So it's really low latency. And yeah, so that was like a very high level introduction. Then this is for a one-to-one call in a more realistic scenario where we have an additional piece, which is called a stand server. And this is being used to be able to communicate also between participants. Is what allows us to know what's the IP address of the other participant, because this is a peer-to-peer communication. yeah, usually you don't know what's the IP address of the other peer, and that's why we use stan. And in even also in some situations, some firewalls might have restrictions, or there can be issues with the configuration of your router. So we have something called a turn server too that allows us to relay the traffic through. So we are able to circumvent the firewall rules, and that's like our worst case scenario. We would be using this, but yeah, this is not being is not hopefully used all the time in video or audio calls. And this is just for one-to-one again. And what happens now if we want to have more participants? So yeah, native peer-to-peer connections is a very beautiful idea, but complicated and not practical when scaling more than 3 to 4 participants, or when you want to process video or do recording. In that case, we need some type of web server. Otherwise, we will have a situation like the diagram I'm showing here at the right, which is called like a mesh network, where all the participants send video and audio to all the rest. And obviously that's not very performant. Each participant here, for example, would be sending like audio and video, like 14 streams each, and there are better ways to do this, and that's what it brings up the idea of the media server. So if we want to scale for larger groups of participants, we have something called WebRTC media servers, and we can scale them, so it's not necessary to have just one. We can have multiple of those, and at some point we can scale not only vertically but also horizontally, and I will get a bit more in depth about this in a few slides. But yeah, in this chart at the right, I'm just showing like a representation of the number of connections we would need in different situations. So if we use a mesh network, we would be the blue line, where we have a linear increase, a 2x increase in number of connections. And then there are other types of media servers that would allow us to have much less connections, which means much less resources for the client, better experience. So one interesting way to build your architecture is just using open source media servers. There are, of course, also paid ones. And here just mention some of the popular open source ones, like Janus, Jitsi, Pyan, MediaSoup, LiveKit. Probably you have heard about some of them in some, like maybe you have even used them for some video conferencing. But yeah, they are used in really large solutions, like could be like Twitter or like large companies are using this. And basically Janus is built in C, Jitsi is in Java, Pyan and LiveKit in Go, and MediaSoup in C++. So you can choose based on the stack they use, but also maybe there are some use cases that are better for a specific one of them. And there are many more, of course. So I mentioned WebRTC media servers, but there are two types of WebRTC media server architectures. And here I want to mention one of them is the MCU architecture. And this, well, means basically multi-point control unit. And what it does is mixing all the audio and video streams in a single server. So as you see in this diagram, there is only one connection going uplink and one downlink. So we have, just 2 streams per user is obviously the best for minimizing resources on the client side, but also is is more CPU intensive, of course, on the server, and requires processing, and also it might add slightly amount of latency, although we are still in the sub-seconds latencies, of course. And these are just some examples of popular open source MCU WebRTC servers, and like FreeSwitch Asterisk that are more popular in the telephony world, and LiveSwitch and Current. And the other type of architecture for WebRTC media servers is the SFU approach. So SFU means selective forwarding unit. And in this case, we are routing the streams through the server, but the server is not mixing them. So we, as a user, I would be sending a single stream or audio and video stream, and that would be distributed to all the participants that need to see or hear that. In this case, you can see then that we have as many downlink videos or audios as participants -1, but we will only have one video uplink. So this is like a middle point between having like a mesh network where you have like many connections, as many as user almost, and the MCU approach where you have just a single stream. The benefits, of course, of this is lower CPU requirements, and also it is possible to do end-to-end encryption. So basically make sure that the audio and video is encrypted all the way, even going through the server. In the case of the MCU, that's not possible because we're mixing, and for mixing, we need that traffic to be unencrypted. And yeah, just some popular open source media servers that are that have an SFU architecture are Jitsi, Janus, LiveKit, and MediaSub. So some of the ones I mentioned before. So how, like now it's nice I talk about like a single media server. So how do we scale beyond like a single server? Like if our, just as an example, media processing is really CPU intensive. So a X large AWS instance could handle maybe 1 or 200 connections. But what happens if we have 1,000 viewers, 1,000 connections required? We would be reaching basically the limit of what would be the vertical scalability of the servers. And this is how you can solve this problem. No? That's one high level representation of how you can do it, by distributing the traffic. So having maybe in this case an SFU, although it could be also an MCU. But we have a server that is like the server receiving video or audio, and it's like the publishing server. And then we have other like subscribing servers that they are going to allow subscribers to listen to that audio or video. So that way we are scaling horizontally, but we need to make sure, yeah, that traffic that goes to the main SFU that we see in this image, it gets distributed or cascade to the other ones. And so that was in the case of the live streaming use case, but this is just another example. In this case, it's not a live streaming use case. This is more like the common large video conferencing solution where we want to see, I don't know, 25, 50 plus participants in the same room. So you might be also, again, reaching the limits of what is the vertical scalability of a server. And it would be a good idea to use an MCU or SFU servers and to be able to connect to both of them simultaneously. So in this case, we can see all these participants, maybe they are in the same room or the same video chat call, but some of them are connecting to one server and others are connecting to another one. And yeah, the benefit of that, of course, is that then we can have more participants. We would be distributing that traffic to the secondary server, and when the main one is full or is at capacity, we would distribute the rest of participants to to the other ones. And there are smarter ways to do this. This is just one approach. So now how we can orchestrate, like those diagrams were really, really high level. One proposed architecture that can be used is something like this one in the image, where we have the 3 main steps, basically. So we have and 3 services. So we have the dispatcher, which is the authentication server, if you want, the one in charge of managing the scaling of the other services, and also distributing the actors or participants. So once we authenticate, the dispatcher decides what to do with that and redirects the user to the right SFU in this case. So you can see here we have group number 1, group number 2. We could have as many groups as we want, but this is represents just scaling peers. So we have the wrapper node, which would be in charge of managing the media server. So how this would work, for example, is I authenticate. I get like a URL that redirects me to a specific group, and then I will start doing the signaling to that specific group. In this diagram is the group number 2. And by signaling, I mean it could be just WebSocket communication that is just exchanging messages, like saying, okay, I'm going to join this session. These are my parameters or my permissions for the session. Maybe some users are allowed to do some specific stuff and others aren't. So that's what would go through, would happen in the wrapper node. And the wrapper node would be in charge of communicating with the SFU and making sure the actor and the SFU can communicate and have video flowing 2 ways. So the actor is sending and receiving from the SFU. That's pretty much how like a establishment of media would go. And there are some challenges if you compare it with other solutions that maybe doesn't need to be low latency. In this case, this is a stateful system. So yeah, you are in a call in a specific session. So any like in this state, there are some complexities there. Also, in this diagram, we try to decouple media service and another logic. So that's why we have something called wrapper node and something called SFU separate. We want that to be decoupled, so the SFU or the MCU, the servers of media, focus on just that, processing media, and the rest, all the business logic is in the wrapper or the dispatcher. So we don't, it's easier to manage and to scale. And something complicated also in this type of applications is auto scaling and being careful also with over provisioning, because yeah, obviously in this case, like because you are in video calls, everything needs to be pretty fast. So if we need to start usually provisioning new services, so spinning up new services very soon, because we might not have time to have them ready when we need them. So that's one pretty complicated issue with WebRTC scaling WebRTC solutions. And also we need to make sure also to not over provision and destroy those or stop those services that we don't need anymore. So for example, if we are increasing at a piece of 2 users per second, we would need to make sure our services are can spin up fast enough to handle those spikes of usage. And again, yeah, talking about scalability in this diagram at the right, I try to define what a basic WebRTC scalability and high availability architecture would look like. Yeah, in this case, is using AWS, but could be any other cloud solution, cloud service. Sorry. And yeah, what we have here is load balancer in that distributes the traffic to the different wrappers. So it's a diagram very similar to the previous one, where we are distributed based on load, and we reach any wrapper, and all of them should have persistence and should know about what session they need to join, and so it shouldn't matter which service I reach. All of them should be aware, and then I should be also able to connect with the RTC media server, and always connect to that one if I need to. So yeah, there are two important points that I wanted to mention when building WebRTC scalable solution is having stickiness and persistence. So we can have sticky sessions by using there are two ways that we have used in the past. Like we can use cookie-based load balance sticky sessions. So in this case, we could make sure that we always reach the same server, and then we are fine. The problem with that approach is that we wouldn't be able to do some of the more advanced architectures, like the ones we were talking about, where we have more than one server for the same session. So where we have servers sending media between them, and in that case, we need some additional logic to make sure that it doesn't matter where we connect. And the other approach is direct routing through initial authentication. So I reach an authentication server. The authentication server tells me where I need to connect, which service within our scaling group I need to connect, and then interact with it all the time. And the data persistence, I mentioned it also a bit, but is basically needed to make sure we can recover. So if a specific wrapper goes down, we should be able to spin up a new one and be able to use that, and that's what is achieved with a scalable database solution. And sometimes doesn't need to be a RDS, could be elastic cache as well, for if we want to focus a bit more on performance. One thing I didn't add here, but that's also common to have, is have some pub/sub mechanisms to decouple some of these. But yeah, this is not shown in the diagram here. So yeah, I talk about the architecture, the stickiness needed, the persistence. So we have that running, but there are other things that can be done and optimized. There are application and media optimizations that you can use to have better quality and have better experience when scaling solutions like this. One way is one tool that we have in WebRTC is called Simulcast, and also SVC. So SVC is a bit newer, and what it does is allows you to send basically like a technique that allows you to encode video streams in multiple layers. So in this image at the right top corner, I kind of describe this, where you are sending different qualities of video, for example, and based on the situation of the network of the clients, some would be able to receive higher quality, and some would be able to receive lower, based on the network conditions. And that's something that is mostly handled by the WebRTC stack. So there isn't much that need to be done, especially if you use media servers. And you can you could choose, for example, based on that, some users would be receiving maybe more frames per second, others less. So That's a pretty powerful option to optimize your WebRTC solution. Also, there is the audio detection, where you can have just audio and display video only when the speaker is interacting. And that's something very common in many applications today. Like, you are not seeing everyone, you just see the main speakers, and we use just audio detection to display that. Or sometimes maybe you don't even need video. So there are other solutions that work pretty good in with just audio, and that's a way also to scale to a much larger audience if needed. Another thing that is commonly used is adaptive bitrate based on resolution of the screen. So, for example, if one of those users in the SVC example minimize the screen, we wouldn't want to be receiving like that much video quality, like the frame per seconds or the resolution of the video maybe doesn't need to be that high. So we reduce it based on the client movement of the screen and the size. And other also pretty cool techniques are the Opus Red and DTX. Those are techniques for audio optimization. And here I explain a little bit how Opus Red works. And is basically a technique of sending redundant audio. So you always send redundant audio in the next package. So if there is a missing packet, we recover it just after. And it's proof that improves audio quality. And yeah, there are some future application optimizations that can be done that they are kind of more in progress. So there is the AV1 video codec that is today being used for very commonly in YouTube for consuming video, or in Netflix, but it's not as popular today for publishing video, just because many of the devices today doesn't come with hardware acceleration for AV1. And that's something that will change and will improve a lot the performance of video calls. And that's something that, well, many people is already experimenting with. And that's one way to improve quality with the same bandwidth. So that's interesting. In similar way, Lyra V2 is an audio codec that does something similar. It's an improved codec that allows similar quality to Opus, which is the current codec being used today. But as we can see in the results here at the right, with much lower bit rates, we are able to achieve same level of quality in audio or score. So playing with those codecs, would make a huge difference, and especially in the future. And there are other machine learning optimizations that will be interesting. They are being used today for noise reduction or packet loss concealment, which what it means is that it fills the blanks of what when we miss a packet, we just fill that with some noise that simulates what it would be, what we would be hearing. So it makes the experience more smooth. So in summary, I would say, like, if you are building like a WebRTC application for scale, first, focus on your use case needs. There are different architectures. There is the FUMC, as I mentioned, but also just once you decide that, also there are different ways to scale it. And you might want to also review if you really need to use low latency streaming, because it's much more complicated than just streaming HLS or some like on-demand video. And so that's something you need to consider if you really need that sub-second latency, and some use cases perhaps don't. Also, don't underestimate the importance of efficient, scalable, and high available WebRTC infrastructure. So um, it's really critical. Like, it's just not going to work if you don't have that set up properly. You want to make sure when you reach a specific amount of connections to make sure you spin up your new service, and if a new service goes down, that we are storing the state and being able to recover from it. And you will need also to decide where you are willing to compromise. So as I was mentioning, you have the for example, the MCU architecture, which puts all the pressure on the server side, and it's a better performance on the client side, or perhaps an SCFU approach, which is a bit more CPU intensive on the client, on the edge, on the user. So you always need to compromise on what you care more about, and if you want to display all the videos or maybe just display one with high quality. So these are some things to consider. And of course, optimize and leverage the latest WebRTC capabilities, that some of them I mentioned today. And I think they also make a huge difference. So yeah, thank you so much. Now you hold the ring of power to build your WebRTC application. And yeah, thank you for listening. I don't know if anyone has any questions.
We do have some questions. So thank you, Alberto, for the presentation.
Yep.
You talked about, let's jump into the question. So you talked a lot about networking, latency, and containers. So there's a question for that. Container technologies like Pivotal Cloud Foundry offer container-to-container networking capability, which helps minimize latency incurred in invoking services remotely. Can you discuss this more and how it can help with service orchestration?
Yeah. I need the first part. Yeah, 1 second. Offer container. Yeah, I haven't specifically used PCF, but yeah. So one issue with low latency is that many people traditionally, it always have been built in physical devices. So it's always that's how many of these media servers were originally built for. And now adding, of course, adding like building them Dockerized and building them in using Kubernetes and things like that facilitates a lot, like the spinning out of the services. But at the same time, there are some unknowns sometimes in terms of networking. There are complexities that, like you are using a virtual machine, and that's something that many developers, like in the team, like you are DevOps, you don't know that much about networking, and network engineer maybe doesn't know that much about DevOps. So it's a point where it's complicated to be very successful with. But yeah, it can help minimize latency by well, it doesn't minimize latency, it minimizes like the spinning up, like the efficiency. I think it's mainly it helps for efficiency reasons. So you don't want to have resources you don't need. But having container technologies or not, it really is not going to change the latency experience on a WebRTC call, because it's just going through the same path. And that's
Okay, thank you for that answer. Anyone, if you have still questions, please ask them in the chat. We have one more here. Do you recommend to use PJSIP library in such applications? So I assume in low latency WebRTC applications.
Yeah, I think PJSIP is a zip library. So this is more of a signaling question. So it just one of the signaling piece. You can use, I'm not familiar specifically with PJC, but you can use any signaling piece that you want. I think the signaling is not usually the problem for real-time applications. The problem is more of how efficient is your media server, and how fast is, like, how close it is to you, and things like that. But really, the signaling communication, you could use PJC, which is, I assume, is using SIP for signaling. You could be using even WebSockets or whatever signaling you want. I don't think that's a critical piece for your architecture, for low latency and for real-time applications. So I would use just what you prefer to send messages.
Okay, thank you for the answer. It doesn't look like we have any other questions right now, so I guess that people will have to reach out to you offline. I mean, probably online, but offline
Yep.
from the conference perspective, and ask those questions if they still have them. Thanks a lot, Alberto, for the presentation, and have fun for the rest of the conference.
Thank you. Yeah, thank you for inviting me. Have a good one. Bye.